So we're starting with Unit 2 then. Our first lesson is an introduction to forces. So this whole unit is actually on forces. We call it dynamics, which is the cause of motion. So a force is also a vector quantity. It has a direction associated to it. And it's basically either a push or a pull. Now we measure forces in units what we call newtons. Just like we measure mass in kilograms, time in seconds, length in meters, forces we measure in newtons. And 1 newton is defined as the force required to have 1 kilogram accelerate at 1 meters per second squared. So 1 newton is defined as 1 kilogram times meters per second squared. Now, we're also going to talk about free body diagrams and something called net force. But first, let's go over the types of forces we can have. There are 4 fundamental forces, meaning any other force you can think of is just one of these 4 forces. I have them listed over here in a little more detail. So we have the strong nuclear force. This is the strongest of the 4 forces. So let's give it a relative strength of 1. But it acts over a very, very small range because it is what holds protons and neutrons together in the nucleus. The next strongest force is the electromagnetic force. It's a little bit weaker than the strong force by about 137 times. And it's responsible to hold atoms and molecules together. It is also responsible for almost all these other forces we see down here, which I'll talk about later. Then we have the weak nuclear force. The weak nuclear force is weak compared to the strong and electromagnetic. And it is involved in radioactive decay, which we will talk more about in our next unit on energy. And lastly, our gravitational force is extremely weak. I mean, look at the order that it's to. 10 to the minus 39. So it's 39 order of magnitudes weaker than the strong force. It is the weakest force that we know of, which is kind of weird because it's the one everybody is so used to the most. It's the one you feel like you interact with every day. Okay, but it's not necessarily true. I mean, if these other forces didn't exist, neither would we. So it's just we don't recognize them on an everyday basis. Okay, so let's look at some of these other forces. But first, I want to tell you what a free body diagram is. So in order to analyze the motion of an object, we need to know what force or forces are acting on that object because forces cause motion. So what is actually pushing and pulling on that object? In order to figure that out, we draw a free body diagram. A free body diagram is basically just a box, right? So something like this, draw a box. That's a terrible box. Okay, and then you would draw all the vectors, all the force vectors that are acting on that object. So that's a very important word, on. It's not all the forces that object puts on other objects. It's just the forces that act on that object. Okay, so for example, you could have this book on a table. So I have a book on a table over here. Okay, so your free body diagram, this is a nice diagram. You don't have to be able to draw a book on a table, but you could draw a box or a dot. And you would draw gravity pulling it down. And then we have this other force called the normal force pushing it up. So what is the normal force? The normal force is perpendicular, that's important, to a surface of contact. So for example, right now, if you're sitting in your chair is exerting a normal force up on you. If you're leaning back in your chair as well, then your chair is also exerting a normal force forward on you, or maybe at some upwards angle. Okay, if I push my hands together like this, right? There's a contact force there as well that we call normal. Now, normal simply means perpendicular. That's why we call these contact forces normal forces. So this book is being pulled down due to gravity, and the table is pushing it up due to that normal force. Now, the normal force isn't a fundamental force. In fact, the normal force is simply due to the electromagnetic force. I mean, there's atoms in the book, there's atoms in the tables, and around those atoms you have clouds of electrons, which is negatively charged. So you have negative charges on the outside of the book and on the outside of the table. They can only get so close to each other, right? So gravity is trying to pull them closer together, but because opposite charges repel, the electromagnetic force is pushing it away. So the normal force is actually just the electromagnetic force. It's also interesting to note that those atoms, even though you have the book on the table, they're not actually touching. There is no actual contact between the atoms, right? What you feel as contact is that electromagnetic force acting on the atoms in your hand if you were pushing on something. Okay, so there's one example. Let's look at another example. So here we have a book on a ramp. Gravity is still going to act down, right? Because gravity always acts down. It's never going to act to the side. Normal is, again, doesn't oppose gravity, because the normal doesn't always necessarily oppose gravity. It's always perpendicular to the surface that it is in contact with. So this case, it's in contact with this ramp. So the normal force would be perpendicular to the ramp. And then if you also have the book sliding, or maybe it's not sliding, there's two types of friction, which we'll talk about in a later lesson. But we have that force of friction, which is opposing the motion. It's opposing that book wanting to, or is sliding down the ramp. So that's one of the other forces we have here, frictional force. Right? It acts parallel to the common surface, the surface that it is in contact with. That's the opposite of the normal force. So the normal force is perpendicular to that surface. Friction is parallel to the surface and in the opposite direction of motion. So if we have this book sliding down the ramp, friction is going to be up the ramp. And friction, just like the normal force, is due to the electromagnetic force. Same thing. In fact, all these forces, except for gravity here at the end, thanks to the electromagnetic force. All right, last example. Here you have a person pushing on a box. That we call the applied force. If you are exerting a force, either a push or a pull on an object with your muscles, we call that the applied force. So in this case, this lady is pushing a box, so there's an applied force forward. Opposing that motion, there's a force of friction backwards. Of course, there's gravity going down, and since it's on the floor, you can't see the floor, but there's a floor there. Right? There's a contact force perpendicular to that floor called the normal force pointing up. There's one other force I haven't mentioned, that's tension. We're going to talk about tension in the next example, but tension occurs if you're using, say, a rope to pull something. There'll be tension in that rope. So before we move on to our example problems on the back, there's one more thing I wanted to talk about, and that's net force. So net force is very, very important to be able to analyze the motion of an object due to the forces. And we'll understand this a little bit more when we get into Newton's laws of motion in our later lessons. But for now, I want you to understand that net force is simply the vector sum of all the forces. So if you have one force up, one force right, one force down, one force to the left, and you add all those together, that is what our net force is. Now you never draw the net force on a free body diagram, because the free body diagram shows the individual forces that act on the object, not the sum of them. So once you have a free body diagram, Then what you could do is look at all those individual forces and add them all together. And that would be your net force. So let's go look at our example problem because it's going to deal with net force. Here we have two people dragging a canoe. Okay, this is like a system diagram. It's not a free body diagram. I'm much better at drawing free body diagrams because it's just a square. I don't think I'd be good at drawing this. I'm a terrible artist. Okay, so two people are dragging a canoe out of a lake onto a beach using light ropes. So they're using ropes to pull it. So those are going to be tension forces. Each person pulls or applies a force of 60 newtons forward. So we have our coordinate system. So just like when we were doing motion equations and questions, we would always attribute a coordinate system showing what direction is going to be positive. This is true whenever you're dealing with any kind of vector. Right? You want to make sure you label a coordinate system so you know what direction is positive, what direction is negative. So we're going to take forward as our positive direction, which is in this direction. And they're each pulling with 60 newtons. So we have 60 newtons on the first rope and 60 newtons on the second rope. Then there is also a force of friction exerted by the beach on the canoe, which is 85 newtons backwards. So we're going to start with a free body diagram. So here's our canoe as a free body diagram. See? That I can draw. And all the individual forces. So we have one, let's call this a tension 1, and it's a vector, is 60 newtons. Okay, I don't really need to write forward because the direction is shown with the arrow here. And then the next one, tension 2, let's call it, is also 60 newtons. And then we have a force of friction. Now this one should be longer. When you draw your free body diagrams, you don't have to draw them to scale, but if one force has a greater magnitude, then the length of that arrow should be longer. So here's our force of friction, which is 85 newtons backwards. Now we need to calculate net force. So this is how we're going to write it. So net force, F subscript net, which is a vector, is the sum of all of these. So it is T1 plus T2 plus our frictional force. So this is 60 newtons forward, so it's going to be positive, 60 newtons. This is 60 newtons forward, so it's going to be positive, 60 newtons. But this is 85 newtons backwards, so I'm going to write it as minus 85 newtons. All right, now I can add them all. So 60 and 60 is 120. Subtract 85, and we get 35 newtons forward. So our net force is therefore 35 newtons forward.